I will begin with a word of prayer once I get up here. So. Dear Heavenly Father, we thank you for your creation that you have richly blessed us with, for who you are. We thank you for this class, and we just pray that you would give us understanding, and I just pray that you be glorified in what we do, Lord. In your name I pray, Lord Jesus. Amen. So, any questions about how the class is structured, anything like that, feel free to type up. I think it'll become clear as we go on. Just to give you like a snapshot of things while I'm getting my markers here, you probably could try to do like, well, the recommended mission one, which is the problem statements are posted, but also the solutions to those are posted on the website, not in Canvas. Because Canvas comes and goes, but the website is forever, as long as I pay that $12 a month, which is probably too much. I need to find a new web host. But so you can try those. That would be good. In the meantime, I would say problem 1, problem 2, problem 4, problem 5. Those jump out as me as ones that we've, already started to look at the methods that you'd solve those with. All right? There's more than that you could do with the methods that we've talked about already. But I need to talk more about conservative vector fields. And so some of this has to do with the the basic problem I posed last time was like, how do you find the integral curve to a vector field, right? So let's just let's review that right quick. So last time, just for reference, we wanted to find if we had f is equal to pq, right? Then if we solve dx dt equals to p and dy dt equals to q, the solution gives parameterization of integral curve. Why did I write integral curve? I could have just used an integral sign there. Oh well. It gives a solution to the integral curve of f, right? The vector field, the curve which lines that's tangential to f, right? And if we don't want a parameterization, we could instead solve this guy. dy dx equals to, well, basically just think about, dy dt over dx dt, but what is that? Well, dy dt was q, right? And dx dt was p. So we could just solve dy dx equals to q over p, or if you like, q dx minus p dy equals to 0, right? You could solve either one of these. These give the integral curve to the vector field f equals to pq, right? Great. So that's just a quick review of what we talked about last class. So then I also talked a little bit about the concept of a level curve, right? And the gradient function. And what I talked about was simply this, that if we look at little function f, right? If we look at little f of x comma y equals to a constant, this is called a level curve, right? And I talked about how the gradient of f, right, which is what? Partial f, partial x, partial f, partial y. I talked about how this is perpendicular to the curve, right? This curve, all right? The gradient vector field is giving you vectors which point perpendicular to the curve, right? So is the gradient vector field, like, let me say it this way, is the level curve to the gradient vector field Is that an integral curve to the vector field? Kind of no. I mean, certainly not. It's the exact opposite, right? It's perpendicular. So the geometry between the gradient vector field and, you know, the level curve is kind of exactly opposite of this setup, right? So let's see here. However, oftentimes we'll run into problems that kind of fall into this category, right? So see if I can work an example. Let's see here. If we look at x squared plus y squared equals to r squared, right? This is a what? A circle, right? So the gradient vector field to this is what? The gradient of x squared plus y squared is 2x, 2y, right? So if I think of if I think of this as a vector field, right? What would the integral curves to that vector field be? So question, you know, can we find the integral curves to this? So let me start out with what we have. What are not the integral curves? What are not the integral curves are x squared plus y squared equals r squared, which are these guys, right? We could be here all day, right? Circles. Well, when there's a quiz, you're going to feel it. Just saying. Because I had a problem last semester with people coming in late to my 8:15. And I thought, how can I fix this? Oh, I know what I can do. I can start a quiz grade. And then I will reward people for being here on time. So nevertheless, there are other things in life that get in the way, I understand, but I'm going to push back in my end with quizzes. So idle threats aside, these are the level curves that are circles. How do we find the integral curves to this vector field f, right? So what do you guys want to do? Let us look at dy dx equals to what? We do 2y over 2x, right? 2y over 2x. And then how do we solve that? Right, so we've got dy over y is equal to dx over x. That's one way we could solve this. Separate, integrate. How's that go? It goes natural log absolute value of y is equal to the natural log the absolute value of x plus a constant, and then we solve that and get y is equal to some constant k e to the x. Oh, my bad. Sorry. This is what happens when I skip steps at this time in the morning. So if I exponentiate both sides, what do I get? Let us not skip the step. So we've got, you know, e to this is e to that, which gives me absolute value of y is equal to e to the c times the absolute value of x, right? Which just gives me y is equal to k times x. So that those curves are the integral curves to the vector field 2x, 2y, right? And that makes sense. If I was to draw those integral curves, I could, right? They're just lines through the origin, right? Like so. And those lines, of course, are the flow lines of the vector field, f, that I've drawn there. And they're also perpendicular to the circles, right? These are orthogonal trajectories, as they're called. An example of orthogonal trajectories. Uh-huh. So you guys told me I should solve this equation by, I should find the integral curves to this vector field by separation of variables. Is there another way? So this method was separation of variables. Another way. We can look at the so-called Pfaffian form of this differential equation. So what do we have? We have, what we have is oh man. Oh, sorry. No, that's there's no other way here. I'm sorry. I'm thinking about the circles, not the lines. Okay, so that's that. Let's look at another example. Example 2, so I find my marker. So this was example 1. Example 2. Let us take a look at the vector field f equals to minus y comma x. All right, let's see if we can find the integral curve to this vector field. All right, so what we'd be looking for, well, let's do it two different ways. We're going to do it the parametric way first. So the parametric way, we'd be having to solve dx dt equals to minus y and dy dt equals to x if we want to find the integral curve. All right? All right. So how would you solve these? We can't just do separation of variables, right? What's the problem? The x equation involves y and the y equation involves x, right? These are coupled. So we'll learn a technique to deal with these in like 2 weeks, but for the moment we just need to kind of be sneaky. And the sneaky thing to do is to plug one into the other, right? So if we plug the first one into the second one, or well, let's see here. No, the other way around. So dy dt is what? I mean, either you plug whichever way you want to go, but ddt of y, what is y? Well, minus dx dt, right? Do you see what I did? All I did was a substitution of the one differential equation into the other. So this right here is y. So I'm just, this differential equation gives me that, right? Emily just cleaned it up a little bit. All we're looking at here is x prime prime equals to minus x, right? That's the differential equation we need to solve for x. So at the moment we don't have a technique, so all we can do is guess, right? Can anybody guess the solution to this? Or did you learn how to solve these in Calculus 2? There's a semester of Calculus 2 I taught how to solve these. It was part of the required curriculum when I was a grad student at NC State. The engineering department wanted us to teach these in Calc 2. It's standard material, actually. They're not hard to solve. Can you guys guess the solution here? What function, when we differentiate twice, gives us back negative of the function?
Sine.
Sine, right. So we'll take your sine and replace it with a r sine of t plus a phase angle, because we don't know where it starts, and so like two constants here. As a general rule of order, for a second order differential equation, you expect two constants, because it's kind of like solving a second order differential equation is like integrating twice. Every time you integrate, you get a constant. So you need two constants in your solution is kind of what we expect. So yeah, but if you differentiate that twice, you get back minus what you started with, right? Now what's y? Now that you guys told me x, right? I'm glad you guys are good guessers. Otherwise we'd been stuck, you know? What's y? Well, notice y is, yeah, negative dx dt, right? So apparently it's minus r cosine of t plus delta. And what is that? That's the parameterization of a what? It's a circle, right? These are the parametric equations of a circle. So continuing example 2 over here. What if we took the other approach, right? What if we solved dy dx equals to, let's see here, x over minus y, right? Of course, we could use separation of variables, right? We could say, aha, well, minus y dy is equal to x dx, separate, integrate, yeah, minus 1 half I squared is equal to 1 half x squared, plus, well, excuse me, minus r squared over 2, obviously, which then gives me that x squared plus y squared equals to r squared are the integral curves of this vector field. Now this is a different vector field than my example 1, right? Example 1, the vector field that we looked at integral curves of is the radial vector field that points radially out from the origin, whereas this one, these vector fields wrap around the origin. Let's see here if I can plot it. Let's see here. If we look at f of like 1, 0, what do we got? Uh, 0, 1, right? So that points like this. How about over here? What is f of what's f of 0, 1 here? We plug in 0, 1. What do we get? Into the formula minus yx, we get minus 1, 0, right? So it goes like this. And then this one will go like this. And I think I better stop. So don't want to get demonetized, you know. So anyway, so now there is a distinction. You're like, well, what does it matter with parametric level? What are the advantages of each? The advantages of the level curve perspective is it's way easier to calculate, right? The advantages of the parametric is that it actually captures the directionality. It captures the directionality of the vector field. See, because the integral curve doesn't have a direction. Like, what's the direction of x squared plus y squared equal r squared? Is it counterclockwise? Is it clockwise? The answer is yes. On the other hand, over here, these are wrapping around in a counterclockwise fashion. All right. So, in other words, the parameterization, they go this way, yeah? And that, of course, aligns with the vector field. If you think about this process of finding the integral curves by taking the ratio of q and p, notice that if we replaced q and p with minus q and minus p, we'd have the same ratio, right? So the level curve perspective doesn't really, the Cartesian perspective, we lose sense of direction. Yeah, the vector field and its negative, they're going to have the same integral curves from the Cartesian perspective. Now there's another way we could do this example. This one, there actually is an alternative method. And that's actually what I want to talk about today. So, alternative calculation, which is, if we look at minus y dy, we're trying to solve equals x dx, right? You're like, well, you did that already. That's true. And if I was going to do separation of variables, which is a perfectly good method here, then I just integrate rates both sides, right? But how about instead of that, I put everything on one side? and I say, okay, well, what I got here is x dx plus y dy is equal to 0. Right? Can I look at this and can I solve it? So do you guys remember from Calculus 3 the definition of the differential? What is the differential of a function of two variables? Do you guys remember? Maybe you don't. Let me remind you. I'll use a different letter here. Definition, if you've got g is a function of two variables. So mathematicians or math majors, whichever you prefer yourself to be called. My apologies for writing this, but by this I mean g is a function of two variables. All right, that's what this means. And in that context, dg is partial g, partial x dx, plus partial g, partial y dy. Right, so this is the differential of g. Okay? And there's a simple theorem, by the way. Theorem. If we look at dg equals to 0 has solution g of x comma y equal to constant. So if we could write our differential equation as the differential of a function, the solution is stupidly simple. I'm sorry, you say we didn't say stupid in our house. You're in my house now, so we say stupid. So sorry, but we need this word if you've watched the news. It's a necessary word. Anyway, so the solution to dg equal to 0 is simply g equal to a constant. This ties into the math I did at the end of class last time. All right? So how about this? Can we write this as the differential of one expression equals to 0? I'm asking you to undo a differentiation. So this is a kind of integration, right? So if you tilt your head and squint, you can see, aha, 1/2 x squared plus 1/2 y squared. See, that choice of g makes this dg. And as such, the solution is 1/2 x squared plus 1/2 y squared equal to constant, which of course is what we found, right? That's exactly what we found with the separation of variables method. But this is another way of thinking about things. So if it's possible to write your differential equation in this way, if you can take a differential equation in Pfaffian form and rewrite it as the total differential of a single function, then the differential equation is said to be an exact equation. Let me state that more precisely here. So definition, if you have m dx plus n dy, if that's equal to dg for some g equal to a function of two variables, all right? Then m dx plus n dy equals to 0 is an exact differential equation. And in this case, and this is a theorem, the solution is g of x comma y equal to a constant. That's it. So simple. So simple. So exact equations are really, really nice to solve if you can understand what the choice is for this g, right? If we can come to an understanding of what the level function is whose solution curves are the solutions of the differential equation. All right, so that's an exact equation. If an equation is not exact, it's said to be inexact. All right? What does this have to do with conservative vector fields? So let me remind you another definition here. F is conservative on U, a subset of Rn, if F is equal to the gradient of some little function f here. This is called the potential function. Right. So this is what we mean for a vector field to be conservative, is if it's the gradient of a potential function. And this has to happen on U. The domain matters here. This notation, guys, this means subset of. So like U is a subset of Rn. Rn is n-dimensional space. Usually we're working in 2 or 3 dimensions, but mathematically it works more generally here. Your question?
I didn't know what that notation was, but I was fine.
Oh, the which one?
After exact.
After exact. Oh, differential equation. Yeah. I'll use that sum in here. So it is true. So I'm veering off my course planner slightly, guys, because I've just found it natural in talking to you to intersperse some comments about like what an exact equation is and what separation of variables is. And as such, I've kind of gotten off task. My task today was supposed to be to do something a little bit different, so we probably won't get quite where I wanted to. In the end, we're going to get to the same place. I'm just saying I'm a little bit off my planner at the moment. I should just not have told you. You wouldn't have noticed. Let's see here. But I want to talk about the connection between conservative vector fields and exact equations. All right, so like it's kind of natural. So like here's an example. Suppose we have vector field F equal to, let us say, y plus, I don't know, x sine of x squared. That's interesting. And then x plus hyperbolic cosine of y. There we go. Hyperbolic cosine has entered the scene. All right. Is this a conservative vector field on the plane? So let's work through that. Is this conservative? On R2. So we're asking the question, can we write this as the gradient of a potential function, right? So what do we have to solve? We need to solve partial f, partial x is y plus x sine of x squared, and partial f, partial y is x plus the hyperbolic cosine of y. Now there are 2 main methods I have to solve such problems. All right. The one method, which I think is usually most successful and easiest, is simply to integrate both of these equations separately and then compare. Right. The other method is to integrate one of the differential equations and then plug it into the other and try to solve it. That one's a little bit more rigorous, that method, because that method will fail when it's impossible. So let's try the more rigorous method for the moment. If we integrate this with respect to x, holding y fixed, what do we get? We get f is equal to xy plus 1/2 cosine of x squared. That's not quite right, is it? What happens when we differentiate this with respect to x? What do you get? You get minus 2x sine of x squared, right? Times the half, which gives us minus x. But I didn't want minus, I wanted plus. So what do? Minus, all right. So the integral of x sine x squared is minus 1/2 cosine x squared. That's a u substitution. And then since we're integrating with respect to x holding y fixed, my constant c1 is technically a function of y. All right? So I integrated the first equation with respect to x. Now what I do, and this is a standard technique, you really should have seen this in Calc 3. If your instructor didn't do this, he has not done his job completely. You should demand a refund. But I'm pretty sure Dr. Wang did this. If you had Dr. Wang. And I'm pretty sure Majeric did it too, if you had him. If you were somewhere else, I have no idea. But anyway, so plug that into here, what happens? What's partial f partial y? We get what? We get x. What's the derivative of 1/2 x, 1/2 cosine x squared with respect to y? 0, right? Partial differentiation. And then we got plus partial c1 partial y equals to what? Equals to x plus cos y. But is the partial derivative notation correct here? I mean, it's not wrong, it's just not right. We could do better because really this is dc1 dy is equal to hyperbolic cosine of y. Right? So then what? Well, then we integrate. What's the integral of cos? Sinh. So we got sinh of y plus c2. And c2 is a genuine constant. So thus, in total, we find f is equal to xy minus 1/2 cosine of x squared plus the sinh of y plus c2. In short, yes, this is a conservative vector field. That is its potential function. All right? If we were to talk about physics, minus this would be its potential energy. Right? And we could show that energy is conserved if this is the net force. We'll actually work that out in here sometime soon. Okay, so then what? What does this have to do with differential equations? It has everything to do with it, see, because there's a corresponding problem of differential equations. What's the corresponding problem of I guess I can write it here. The corresponding problem of differential equations, I think I got room, is example 4, solve parentheses y plus x sine of x squared dx plus x plus cos of y dy equals to 0. Can we solve this differential equation? Question? Okay. So, I mean, can we solve this differential equation?
My car's getting towed, so I gotta...
Oh, car getting towed. Yeah. No. By all means. Sorry about your money. Yeah. It used to be like $390 to get a particular pass here, and then I found a spot to park in, and parked in like 2 months. I didn't get towed, and then one day my car wasn't there. I was like, what? At the time, it was $90, and I thought, it was worth it, you know, because it was still cheaper than getting the thing. But anyway, it was a really nice spot too. It was like right out in front of the building. But yeah. So this, okay. So first of all, what would you not be successful here? My point Separation of variables, does it work here? Think about separation of variables. If you do separation of variables, you got a ratio of functions of x and functions of y. There's no way you can separate x and y here. If you look at the fraction you'd be faced with, it's nasty. You can't undo it. It's all intertwangled. But this is easy to solve because this is exactly the differential of xy minus 1/2 cosine of x squared plus the sinh of y. Drop the constant. You know, we don't need it. In other words, this is an exact equation. Because the coefficients of the differential equation, the m and n, correspond to the components of a conservative vector field. You see there's a relation between the total differential and the gradient. Right? There's an interplay here between the gradient being a vector field and a differential expression, a Faffian form, if you will, a differential form, being the total derivative of a function. I can state that more clearly, but the solution here, so the solution is just xy minus 1/2 cosine of x squared plus the hyperbolic sine of y equals to a constant. There you go. Them's your solutions, done. Now, I did the work for example 4 and example 3, right? Right? Yeah. So let me state a theorem here just to try to make it precise, because I'm talking about two different ideas at the same time, and it's a little bit easy to get confused sometimes. So the theorem is this: m dx plus n dy equals to 0 is an exact equation on U, a subset of R2, if the vector field f equals to m comma n is equal to the gradient of g for some, or we could put it, let me use the little f here. It doesn't have to be g. You know, you could use the little f, you could use the little g. Like I don't have a, whatever. It's equal to the gradient of little f for some f on U. In other words, an exact equation is one for which the coefficients of the differential equation, the m and n, correspond to a conservative vector field. And since you guys know how to find the potential function for a conservative vector field from calculus 3, right? You learned that already. You can solve these, right? Now, if every differential equation was an exact equation, well then there'd be hardly anything to teach you, right? You just always do this. But is every differential equation an exact equation? You probably can guess from my question that the answer is no, right? How do we decide whether or not a given differential equation is in fact an exact equation? Any ideas? Like, well, I've erased it, but see, in my earlier this lecture, I started trying to make my example 1, I think, like an exact equation. And I was like, wait a minute, what? Oh, no. So it didn't work, right? Let's go back to that. Let's see why that equation was not exact. If we go back to example 1, which was what? So in retrospect, we were solving dy dx equals to, what was it? I can't remember. Is it y over x or is it x over y? It was y over x. It's the one that gave us natural log absolute value y equals natural log absolute value x plus a constant. Then we exponentiated, we got y equals to kx, or the solution set the lines through the origin. By the way, there was something there I missed. I should have talked about an exceptional solution, right? Like there's also x equals to 0 is a solution to that. The vertical line is a line through the origin, which the differential equation admits, although it depends on how you write it, you know? Like this differential equation x equals to 0, not solution, right? But on the other hand, if I write y dx minus x dy equals to 0, x identically equal to 0 is solution. This just means identically equal to 0, all right? But that solution's not a function. So this begs a larger question, which is like, what do we allow to be a solution in here, right? So the philosophy is this. There are two kinds of solutions. There's implicit solutions. There's explicit solutions. Explicit solutions are ones which are functions. Implicit solutions could be defined by an equation. We'll be talking about this a lot more. I'm just throwing the terminology out here today. So sometimes we'll lose one of the implicit solutions or even the explicit solutions because when we go from the Pfaffian form, like this, to the quotient form, there's some division, and that division, in that division we lose a solution, right? So in the past I've called these extraneous solutions. That's not really quite right because extraneous solutions are not even part of the solution set. I often tell students if I was to be a rapper I would be extraneous G because my tagline would be, hey, I'm extraneous G, and I'm not even in the solution set, you know. But so really I just called them extraneous as an excuse to tell that stupid joke. Although I've been told that there's a comment on Rate My Professors which says that my jokes aren't funny. It's a deeply hurtful comment. How dare they? I already know they're not funny. That's what makes them funny. So this right here, though, is this an exact equation? So here you've got, in other words, can you write y is equal to partial f partial x, right? And can you write minus x is equal to partial f partial y? That's what it would take for this, if this, you know, if, let me do it in a different color here. If df is equal to this, then this has to happen. Is this implication a worthy one, or is it an impossibility? Can partial f partial x be y, and can partial f partial y be x minus x? Well, there's also a second partial derivative, right? So we can calculate partial partial y of partial f partial x is partial y versus partial partial x of partial f partial y equals to partial partial x of minus x. So let me put this in the other notation. This is fyx equals to 1. This is fxy equals to minus 1. Or maybe the opposite way around. Let me think about that for a second. The notation, the subscripts get flippity-flopped. My bad. But anyway, it doesn't really matter. Because what do we know about mixed partial derivatives? You remember? They have to be what? What is the relation between the xy derivative and the yx derivative? They're what? Equal. That's a problem. Because if the xy and the yx derivatives are equal, what do we get? One equals to minus 1. Oh, oops. Right? So apparently, y dx minus x dy equals to 0 is inexact. It's not an exact equation. Yep.
Why is it negative x equals df dy not x?
Because there's a minus right here.
Why is that part simple?
Why is that part? Because we look at m dx plus n dy. I mean, this has to be the differential of f. I mean, I can't just ignore the minus. It's part of it. I'm not sure I'm processing your question correctly yet.
Not sure the word. Okay.
Okay. So this suggests a little theorem, right? Because we could do this calculation on any possible differential equation, right? There's a simple test. This is the so-called closed condition. So, theorem, if partial m partial y is not equal to partial n partial x, then m dx plus n dy is not equal to df for some f. So we can check ahead of time. We can check, do the derivative of the x component with respect to y match the derivative of the y component, the y coefficient with respect to x. If they're not matching, it cannot be an exact differential equation. Now, next lecture, I'm going to dive into this rather deeply and talk about how this relates to the structure of conservative vector fields. All right? And we're going to understand what this has to do with like Green's theorem and some other things that you learned in Calculus 3. All right? And also I'm going to introduce something called the exterior derivative in differential forms, which I hope you'll find interesting. Anyway, I think that's it for today. Thanks, guys.